All right, I want to do an example for everyone that's to help some more with the moment and the forces and that sort of stuff. So we're going to do this. Let's get this page expanded here. Make sure I'm using black, and I think I'll use a ruler to start with. All right, we're going to have this diagram, and then I'll tell you exactly what we're looking at here in the long run. But this is an old example I've done for years, but I'm not so sure I remember how I went about it, so we're going to do it for you guys. We have this, and then I'm going to do this, and we'll put this in green because this is a cable, if I remember right on this problem, out to here. Alright, and it is this. So you go away for a minute. We have point C up here, we have point D down here. Technically this would be some point that pivots, like so, grounded out. This is an anchor point. We're going to call this one E. And then somewhere in this problem, I'm not sure why it did this, but I'm going to put them in anyways. We got point A, and we got point B. This may have just been some combination problem that I had in the beginning, or that was part of an example I used once. But for this, we got a force here. We're going to call it T BC, and then we're going to do get over there. I'm going to call this one TAC. All right. And the things that we know are this. So given, we know the tension in BC is equal to 1,040 newtons. All right, and we know a few more things here. So let's put these in blue, and they are the distances between things. And I'm going to do this one here. There and over here at E. Oops, don't slide around on me. Okay, so in those we have 0.875 meters. Alright, we have here 0.2 meters, and definitely nothing in this is to scale. So bear with me here. And then we're 1.9 meters there. Alright, I'm going to cheat. We'll just do this. And those are our distances. Did I miss anything? Oh, we got some theta angle down here that references to the ground, and we are relatively good. Yeah, okay. Alright, what we're looking for, let me get rid of the ruler. Find the moment about, not B, D, about D. Okay. Okay, so this is a great problem from the standpoint of we have no idea where to start. I do because I'm looking at my solution, but as if I was a student and I was looking at this, it's like I just don't know where to start. I really don't. And I remember doing problems like this as a student thinking to myself, geez, this is just entirely crazy. So here's a few things you can do. Ask yourself some simple questions. Um, and I now can I see simple geometry in this? Okay. You're looking for a square. You're looking for a triangle. Nuts. You could even looking for a circle. I've never seen a circle that really plays out well for this kind of stuff. But generally, you're looking to see what you can see from the way this problem's laid out for you. In this particular case, I see a triangle. If I was to take C and draw vertically down to this point here, let's call it, yeah, I'll call it D primed for some lack of better letter to put on it. No, I'll call it F. We're not using F for anything. So I have point F right here that if I draw from F to C and then F to E and then E to C, I got a right triangle. So cool, that helps me sort out what's going on. So then what I really need to know is based on triangle ECF, what do I know? Okay. Gee, that's a really crappy way to spell. Let's clean this up. What do I know? Well, I know I could figure out what the EF line is. All right, and that's going to be equal to 1.9 meters plus 0.2 meters, and I should get an answer of 2.1 meters. And I know what CF is. Cool. Can I find what's going on elsewhere with that? Yeah, I could go find EC. Not so sure I need that. But they didn't give me an angle here of theta. I do need theta. So let's go find theta. So if I know theta, or if I need to find theta in this case, but I know the sides of the two triangles, all right, why not do it that way? So tangent of theta is equal to 0.875, so the opposite over the adjacent side of 2.1 meters. And a little bit of math here. I will write it out just for the sanity of making sure everybody knows what we're doing. Let's clean that up. And we get all done. We get theta is 22.6 degrees. Okay, so that's one portion of the answer. That helps us quite a bit. Now, the other things that we know, well, outside of the dimensions, and we now know theta. Okay, so we have that as 22.6. We know that BC had a tension in it of 1,040 newtons. Okay, so the EC had some larger tension in it because we also have a tension TAC that goes down. Okay, and I'm still not sure why in the world A and B are located out on there, but we're just going to call it what I call it here. Okay. Okay, so the next piece is this. Go back to some geometry. So if I have a point here, and I have T, BC here, and I have T, AC there. All right, and then I come back down this way. All right. Ah, I see what I'm doing wrong. This is TBC in the Y, and this is in the X. Ha ha ha. Okay, TBCX. No, take that back. That goes there. This is X. This has got to change to BCY. Okay, and that makes more sense. So attention TB or T sub BC is 10,040. Okay, follow along. Back down to here. God, it'd be nice if I could read my own writing. DBC equals 1,040 newtons. Okay, we don't know that one, and we don't know that one. We would probably like to know those. They'll help us solve some things along the way. Okay. Now, here's the fun. So let's do this. Remember this from geometry once upon a time? If I have theta here, which is 22.6 degrees in this problem, I also have theta there. Okay, so opposite sides of two parallel, the angle of two parallel planes intersected by a diagonal create equal and opposite angles, or something like that, if you go back and look up the math definition. Okay, and then we are pretty much good to go here. Okay, so with that we can find TBCX and then find TBCY. Okay, and that is going to be fairly simple. Okay, so if we do this, we're going to do TBCX is equal to TBC cosine of theta. And let's just make sure that I got this right. So theta is here. Anything with cosine has to be the adjacent side. So I am looking for the x. All right. So 1040 newtons cosine of 22.6 degrees. And when we get all said and done, we are 960 newtons. Okay. Now we want to find TBC y. It's TBC sine of theta 1040 sine of 22.6 degrees. And probably wouldn't hurt if someone got a calculator out and checked this, but it's 400 newtons according to my notes. Okay, cool. So what have we found? Well, we found that, we found that, we know the angle, and what we're really still looking for is what's the moment about this plane right here, or about D. Okay, we can find that, and this is relatively easy. Doesn't get involved in any ij's or k's, it's just two-dimensional. So let's do this. And I'm going to assume, nope, still in red, sorry. Assume that the moment is positive in this direction. We're going to write the sum of the moments about D is equal to minus TBCX times 0.875 meters and minus, and I'll come back and explain the minus signs here in a second. 0.2, that's not right. That 0.2 meters. Yeah, it is. Okay. All right. Now, assuming that it goes back up here, that it's positive in this direction, we have a negative BC going to the left because we have always make the assumption that that's a positive y and that's a positive x, and then we can get our solution. So TBC y here is negative, TBC x is negative, thus we get these two guys. Okay. 0.87 is the vertical distance from D acting on X. So let me do a little diagram here. Or am I going to do this? I'm going to do it over here. No, I'm going to do it right here underneath this. So here's my point D, and here's my TBC X acting at C. So it is offset by the 0.875 meters from here to there. Okay, so that's what that one is. And this one, D's here, C's there, and we're looking at TBC Y here, and it is from D to C is 0.2 meters. Okay, and that's the distance between here and there. Okay, so that's what that's about, and that's where that came from. Hopefully you see that same picture the way I see it. If not, ask some questions, be glad to help answer it. But we are now at the point where it should be fairly simple to plug some numbers in. So we have a negative 9, I already wrote the equation out, 960 newtons for B of C of x times 0.875 meters minus the 400 newtons of the B of CY times the 0.2 meter offset from D, and when we're done it turns out to be a negative 760 Newton meters. Okay, and if you get the negative sign here, so here's the red stuff, this negative sign means I chose the direction wrong. So the moment about D equals 760 Newton meters in that direction. So it becomes counterclockwise. Okay? And that's all that means. Simple. That's the solution to that problem. So quick review on this just to make sure everybody's with me. It's how to set the problem up. It's how to see what you don't really see when you're given the problem. Look for the geometry bits. Okay? And then based on that, what can you solve for? And then the next piece is what's the obvious thing that's missing that I may need down the road. And if you can ask yourself that question, you're going to be able to do almost anything in engineering. You just need to start asking simple questions. What do I have? What do I go? And where am I going to go with it? Okay, I'm going to stop the video. I'll see you in the next one.